In this question, we're asked for the molecular orbital diagram using the linear combination of atomic orbitals for O2. And it asks us to include any core electrons. So here, you don't need the atomic orbitals, but I do want to show them here so that it's more obvious what's going on, or the explanation makes more sense. So first, we're going to draw two oxygens. So one here and one here. And then we're going to draw their atomic orbitals. So oxygen is 1s2, 2s2, 2p4. That is simply the electron configuration of oxygen. Of course, the other oxygen is the same. 1s2, 2s2, 2p4, like so. Now we want to combine these atomic orbitals into molecular orbitals. And we can have regions of constructive interference, which are lower in energy, and regions of destructive interference that are higher in energy. S orbitals can only form sigma bonds. So this is a sigma 1s, where it's lowered in energy, and this is a sigma star 1s, where it's higher. So bonding and anti-bonding, or constructive interference and destructive interference. It's the same for a 2s orbital. We can have a sigma 2s, lower in energy, and a sigma star 2s, higher in energy. So bonding and anti-bonding, constructive interference, and destructive interference. Finally, for a p, we can have multiple orbitals. So for p orbitals, we can have both sigma and pi. For oxygen and fluorine, the sigma 2p is lower in energy than the pi 2p. But for nitrogen, the pi 2p is lower. So the first constructive interference is the sigma, and then there's a pi 2p, which is actually two orbitals. So if you have 3 atomic orbitals, you must have 3 molecular orbitals. Or if you have a total of 6 atomic orbitals, you must have 6 molecular orbitals. For antibonding, the pi star 2p is here, and the sigma star 2p is here. So we have constructive and destructive interference. These are the only orbitals that you need to place on your diagram. And again, if you have something like nitrogen, or smaller, carbon, these two are flipped. So the sigma is higher in energy than the pi for the bonding. So next, we need to put in the electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons from this oxygen, and 8 electrons from this oxygen, so we need to put in all 16 electrons. So note, we have the exact same number of molecular orbitals as we had atomic orbitals, and now we got to put in the same number of electrons, 16. So if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And what you'll find is that actually oxygen is paramagnetic. And if you were to do the bond order, which is subtract all the electrons in the bonding orbitals, and then subtract from that number the number of electrons in the anti-bonding orbitals, and divide by 2, you would find that the bond order is 2. So essentially what's in the middle here is what is required to answer this question.